When you think of engineering, you probably picture people in hard hats building massive bridges or programmers writing code, and that's part of it. But at its heart, engineering is simply the act of solving human problems. That phone in your pocket, that's a solution to the problem of long-distance communication. That chair you're sitting in, a solution to the problem of gravity makes my legs tired. Engineers use science, math, and a whole lot of creativity to make our lives better, safer, and easier. Our goal for this lesson is to learn the first and most critical step in that whole process. This standard, HS-ETS11, is all about how you define a problem. We're going to take a big, messy, major global challenge, like climate change or world hunger, and analyze it. That means we'll break it down into a clear set of rules. We'll list the criteria, which are the must-haves for a good solution. We'll identify the constraints, which are the limits like money and time. And we'll do all of this while remembering who we're solving the problem for, the people with all their needs and wants. This first step is part of a bigger process that all engineers use, called the engineering design process. You can think of it like a recipe. You have to define the problem first. That's like reading the recipe and understanding what you're trying to bake. You can't just jump to building a prototype, step 3, without brainstorming, step 2, or even knowing what you're supposed to be building, step 1. If you skip this first step, you're guaranteed to waste time and money building the wrong thing. We're not just solving small problems. This standard asks us to look at major global challenges. These are the biggest, toughest, most complex issues facing humanity. These are problems like, how do we make sure every person on Earth has clean water to drink? Or how do we stop pumping so much CO2 into the atmosphere? They are huge, scary problems. But the only way to solve a giant problem is to break it down into smaller, solvable pieces. This brings us back to step 1. Why do we spend so much time just defining the problem? Imagine your parents tell you to build a house. You could spend a year building a beautiful 2-story, 5-bedroom house. But what if they just needed a small 1-room shed for the lawnmower? You built a fantastic solution to the wrong problem. Defining the problem means you stop and ask the right questions. Who is this for? Why do they need it? What is the real root cause? You have to be a detective before you can be an engineer. A huge part of being a detective is figuring out what people truly need versus what they just want. A need is a must-have: clean water, safe shelter, enough food. A want is a nice-to-have: a cool-looking design, extra features, convenience. When you're designing a solution for a major global challenge, you have to focus on the needs first. If you're designing an emergency shelter, its need is to be safe from the storm. Its want might be to have Wi-Fi. You have to solve for safety before you solve for Wi-Fi. To know if you've met those needs, you set up criteria. Criteria are just the rules for success. It's the list of things your solution must do to be considered a success. Think of it this way. If your solution was taking a test, the criteria are the questions on that test. To get an A, you have to answer all the questions correctly. Without criteria, you have no way of knowing if your design is any good. We can split criteria into 2 types. The first is qualitative. These are based on qualities or characteristics. You can't easily put a number on them, but you know them when you see them. Is the solution easy to use? Think about a well-designed app versus a confusing one. Is it safe? A new car design must pass safety tests. Is it durable? You don't want it to break the first time you use it. These are all pass-fail observations. The second type is quantitative, and this is where the math comes in. Quantitative means quantity, or numbers. These are the criteria that you can and must measure. If you're designing a new backpack, your criteria might be, must be able to hold 20 pounds of books, and must cost less than $50. If you're designing a water filter, it must purify 10 liters of water per day and must be 99.9% effective at killing germs. These numbers are not suggestions, they are hard targets. Now, on the other side, we have constraints. If criteria are the goals you're aiming for, constraints are the limits that are stopping you. They are the rules of the game. You might want to build a bridge out of a super strong, lightweight fantasy metal, but your constraint is that you can only use steel and concrete. Constraints aren't bad, they are actually what make engineering so creative. They force you to find a clever solution inside the box. The three most common constraints you'll always face are time, money, and materials. Time. You almost never have forever. You have a deadline. Your project is due in 6 weeks. Money. You almost never have unlimited money. You have a budget. Your solution can't cost more than $500. Materials. You can only build with what you can get. An engineer in Chicago has different materials available than an engineer in a remote village in the Amazon. Besides the big three, there are all sorts of hidden constraints. Technical constraints? Is this even possible? Does the technology exist, or do you have to invent it? Environmental constraints. Your solution can't create a new pollution problem. And, most importantly, social and ethical constraints. Is your solution fair to everyone? Does it respect the local culture and laws? You can't build a new factory if it means bulldozing a historic cemetery. That's a social constraint. Let's put this all together with a case study. Let's pick one of those major global challenges. Access to clean drinking water. Billions of people get their water from sources that are contaminated with dangerous bacteria and viruses. It's a huge, complex problem. We can't solve it for all 2 billion people at once. So the first step of defining the problem is to narrow it down to a specific group. Let's analyze the problem for one specific community, a rural village where the only water source is a river contaminated with bacteria, like E. coli. The problem isn't just no water. The problem is that the water they do have makes them sick, especially kids. So our first simple problem statement is, we need to find a way to make this contaminated river water safe for the villagers to drink. That's a good start, but now we need to add our rules. Let's set the criteria, the grading rubric for our solution. A good filter for this village must meet these targets. Let's set some quantitative, number criteria. It must produce at least 10 liters of water per day, enough for one family, and it must remove 99.9% of bacteria. And let's add some qualitative, quality criteria. It has to be easy to clean, and it can't make the water taste bad, or people won't use it. Now, what are our constraints? What limits do we have in this specific village? This is key. We can't just ship them a $1,000 high-tech filter. So, money. The solution must cost less than $20. Materials. This is a big one. It must be buildable from things you can find nearby, like sand, gravel, clay pots, or plastic buckets. Technical. There's no electricity, so our solution has to be 100% gravity powered. Finally, we have to consider the societal needs and wants. The need is obvious, safe water to prevent disease. But what about the wants? The villagers might want something that isn't heavy to carry. If the filter is hard to use or breaks easily, people will stop using it, and the solution will be a failure. So a societal constraint is that the solution must be simple to maintain. If it requires a $50 replacement part from another country, it's a failed design for this community. Now we put it all together into one beautiful problem statement. This is the final product of our analysis. It combines everything we just did. Here it is. Design a water filter for a rural village that removes 99.9% of bacteria and costs less than $20, using only local materials and no electricity, in order to reduce waterborne diseases. See? It's a complete instruction manual. An engineer can take that statement and know exactly what they need to build. Why do we go to all this trouble? Because a vague problem leads to a vague solution. If you just say, make a better car, what does that even mean? Faster, safer, cheaper? A well-defined problem is like a clear target. Design a $15,000 electric car for city commuters that is safer than any other car in its class. Now I know what to do. Defining the problem is how you aim before you shoot. So this is your job as a 9th grade engineer. Before you ever touch a piece of building material, you have to think. You start with that big global challenge. You narrow it down and define the specific problem for a specific group of people. Then you list your rules, the criteria, what it must do, and the constraints, your limits. And you never forget the societal needs of the people you're designing for. If you can do this, you've already done the hardest and most important part of engineering.